we get to vectors and matrices and the like, I'll present some basic mathematical definitions and notations that we're going to use throughout the course. A lot of these that you may already know, so feel free to go through them very quickly or skip over parts you know. A set is an unordered collection of objects. So spades, so hearts, spades, clubs, and diamonds. The order doesn't matter. We use this symbol to mean that an element belongs to a set. So the heart belongs to this set. This means that A is a subset of B. What that means is that every element of the set A is also an element of B. And we say two sets are equal if every element of one is an element of the other. Remember, the order doesn't matter. And a convenient way to prove that two sets are equal is to prove that each is a subset of the other. And the proof usually has that form. First, you'd prove that A is a subset of B, and then you'd prove that B is a subset of A. Here's a notation that we're going to use a lot. Call it a set expression. The set of non-negative numbers would be written like this. The set of all numbers x in the real numbers such that x is greater than or equal to 0. So I use the colon to mean such that. So there are two parts to this expression. The part before the colon, which tells us where these elements come from, and introduces a variable to refer to them so that I can impose conditions in the second part. The second part gives a rule or constraints or conditions that say which of these elements belong to the whole set. There's an analogous Python expression. Let's say this set S is defined to be these integers. The expression x for x in S if x is greater than or equal to 0 gives you only the elements of S that are non-negative. Very often, instead of writing this, we'd write just this. We'd leave out the part that specifies that x is a member of the real numbers if it's supposed to be clear to you that that's where these numbers x are coming from. Here's another example. The set of x such that x squared minus 5 over 6 times x plus 1/6 equals 0. Implicitly, we're talking about real numbers x. And this set consists of just two numbers, 1/2 and 1/3. If a set S is not infinite, we use these vertical bars to denote the number of elements in the set. It's called the cardinality of the set. For example, this set has cardinality 4. Now I introduce the Cartesian product. Given sets A and B, the Cartesian product of A and B is the set of all pairs little a, little b, where little a belongs to big A and little b belongs to big B. So here's an example. We can take the Cartesian product of the set consisting of 1, 2, and the set consisting of hearts, spades, clubs, and diamonds. The Cartesian product is the set of all these pairs. This is named for Descartes, and we'll see him later on in the course. So for example, what's the cardinality of the Cartesian product of A with B in this case? Well, we have two choices for the element of big A and four choices for the element of big B, so we end up with 8 in total. There's a simple rule that if A and B are finite sets, the cardinality of the Cartesian product is the product of the cardinalities of the two sets. Using this, what's the cardinality of this Cartesian product? There are 13 elements in this set and 4 elements in this set. So the cardinality of the Cartesian product is 52. This expression denotes the set of all pairs of real numbers in which the second equals the square of the first. And of course, we might abbreviate that in this way, leaving out this part. So just the set of pairs x, y such that y equals x squared. You're supposed to guess from the context that x and y are elements of the real number. Here's another example. the set expression tells us that the set consists of all triples x, y, and z, where x, y, and z are elements of the real numbers, such that x is greater than 0 and y is greater than 0 and z is greater than 0. That is, it's the set of all triples of non-negative real numbers. You're supposed to interpret the comma here as an and. All the conditions on the right have to be satisfied for the triple to belong to the set. And as before, we might abbreviate that by leaving out this part and write it in this way. What's a function? Well, intuitively, a function for each input element in a set A, a function assigns a single output from another set, B. And in this context, A is called the domain of the function, and B is called the codomain. Formally, in math, a function is often defined as a set of pairs AB, no two of which have the same first element, A. So here's an example. The function with domain 1, 2, 3, and so on that doubles its input is represented by this set of pairs. The first element of the set is the pair 1, 2. The second is 2, 4, and so on. Here's another example. In this case, the domain is the Cartesian product of the positive integers with itself. And this function involves multiplying the two elements that form its input. So 2 times 2 is 4, 2 times 3 is 6, and so on. Now, the output for a given input is called the image of that input under the function. The image of q under the function f is denoted f of q. This should all be very familiar. And we would say that if f of q equals r, we say that q maps to r under f. In Mathes, we write it this way. Q maps to R. So this symbol represents maps to. Now remember that the set from which the outputs are all chosen is the codomain. We use this notation to mean that f is a function whose domain is D and whose codomain is f. Now we have some flexibility in defining a function as to the choice of the codomain. We're allowed to have elements in the codomain that are not images of any elements in the domain. Here's a quick example. Caesar crypto system. The Caesar cipher. Each letter is mapped to the one 3 steps ahead. So matrix would map to Pudwala. So the function mapping letter to letter can be written in this way. It maps A to D, B to E, C to F, and so on. And we might use a diagram like this to represent that same function. A maps to D, B maps to E, and so on. In this case, both the domain and the codomain are the letters A through Z. Now, the image of a function is the set of all the images of the inputs, the images of elements of the domain. It's written im of f. For example, the cosine function. We can define the cosine function to have the domain, the set of real numbers, and the codomain also the set of real numbers. However, the image of the cosine function is just those real numbers that lie between -1 and 1, because those are the only numbers that are the images under the function cosine of elements of the domain. And notice that the image in this case is not the same as the codomain. Now, the image of the Caesar encryption function is A through Z, which is the same as the codomain. Here's another example depicted here. The domain is the numbers 1 through 4, and the codomain is A, B, C, D, and E. And you notice the image of this function is the set A, B, C, and E. D is not in the image because there's no element of the domain that maps to it. You might be familiar with the term range. Some people use range to mean the codomain of a function, and some people use range to mean the image.